So hello everyone, I am Xinrui, Head of Technology at Taiyang. So I will be moderating the conference further. So our next presentation is from Jietai. They call themselves as JTPV. So we have Xinrui An, who is an R&D manager at Jietai. He is going to talk on the cooperation to assemble high-quality modules using N-type solar cells. So in a nutshell, he's going to tell us how to treat the cells from JTPV in module factories, taking the perspective of cells are the materials for the module production. So the floor is yours.
Thank you. Thank you. Good morning, ladies and gentlemen. I'm Xinrui from Jietai Solar, and it's a great honor for me to share our N-type cell technologies and some prospects on high-quality modules here today. Today's talk will cover the following sections. I'll first give a bit of update on the global renewable energy and PV market trends, followed by some background information about our company, Jietai Solar. Then I'll discuss in detail about our N-type cell technologies and give some prospects on module technologies from a cell manufacturer's point of view. And finally, I'll share some results about our latest half-cut cell and edge passivation technology, which could be quite interesting for module suppliers. Renewable energy has a vast market ahead. More than 100 countries reached an important agreement at COP28 and set up the goal of tripling global renewable energy capacity to 11,000 gigawatts by 2030. For solar PV, the goal is over 5,400 gigawatts by 2030, 5 times the current amount, and will account for nearly half of total renewable energy capacity. Photovoltaics is therefore expanding at an unprecedented speed. According to the IEA forecast, in terms of global cumulative installed capacity, solar PV will exceed hydropower in 2024, natural gas in 2026, and coal in 2027 to become the largest single energy type. In terms of electricity generation, the share of PV is also expanding very rapidly. It will exceed wind in 2024, and by 2028, renewable energy sources altogether will account for nearly half of total electricity generated. In 2023, the PV market, the PV module price dropped below 1 Chinese yuan per watt, further accelerating global PV installation. The total global installed capacity reached 435 gigawatts, to which mainland China contributed about 50%, according to Bloomberg. And annual installation will continue to rise, and the total installed capacity by 2030 will be in good accordance with the goal set up at COP28, as you can see from the chart. In terms of cell technology, we are in the transitional stage between PERC and TOPCon. P-type PERC has been the dominating cell technology for nearly 5 years, but 2023 marked the rise of N-type TOPCon. And according to PV InfoLink, its market share will almost certainly exceed PERC by 2024 and remain high for the next few years. Other emerging cell types such as HET and BC will also have various market share in the future. Now please allow me to briefly introduce our company, Jietai Solar, to you. Jietai Solar is a wholly owned subsidiary of Xinrui, a China Asia-listed company. We are a professional solar cell manufacturer with N-type capacity over 40 gigawatt and PERC capacity about 9.5 gigawatt. Last year saw the rapid growth of our business, both in terms of revenue and net profit, thanks to the booming market for N-type modules. In 2023, Jietai ranked #1 globally in terms of N-type solar cell shipment. While the top 5 combined shipments were 35 gigawatt, Jietai alone contributed 20 gigawatt. Now I'd like to share some of our advanced N-type cell technologies, including stack wafer depot process, selective emitter, and emitter metal contact optimization, which is also known as SE+. The stack wafer depot technique can be used in several different tube processes. It basically enables a pair of wafers to sit face-to-face or back-to-back, depending on the process site in the tube. The desired film can be grown on the exposed side of the wafer, with slight wraparound around the edges of the inner side. These high-temperature processes are usually followed by a single-sided wet chemical etch, during which the unwanted wraparound layer can be removed. The benefit of stack wafer depot is quite obvious. We can double our production capacity compared to standard double-side processes. However, it does require a bit of technical finesse in doing so. First of all, we had to tune our recipe to accommodate for the doubled quantity of wafers for more uniform diffusion or deposition. We also had to deal with the peripheral wraparound layer very carefully, because in some cases, it could be quite tricky to remove without destroying the underlying layers at the center of the wafer. And this can be done by optimizing the subsequent wet chemical etch process. And the last but not least, we also had to deal with the surface stress buildup due to single-side deposition of films. And this was achieved with a slower deposition rate. We successfully overcame all the challenges and incorporated the stack wafer depot technique in all high-temperature processes. The second important technology embedded in our N-type cells is the boron selective emitter. The traditional silver aluminum paste used for front metallization on N-type cells form silver aluminum spikes upon firing to form ohmic contact. And deep penetration of these spikes into the dielectric layer, however, can cause significant recombination in the contact region. And this can lead to VOC or efficiency losses. Okay. So for the third technology, which is the emitter metal contact optimization, also known as SE+, we basically it's like a plus version of the selective emitter. We kind of developed this technology to reduce the size and penetration of the aforementioned silicon aluminum spikes through the tuning of the paste corrosiveness in conjunction with optimized firing conditions. And this can make the penetration of silver aluminum spikes more shallow and smaller into the dielectric layer. Therefore, with this technology, we can increase the cell VOC and efficiency with substantially reduced contact recombination. And our N-type cells also have several other features widely adopted in the industry. Aluminum oxide and silicon nitride stack is often used for the front-side passivation and for an anti-reflection. And the use of gradient indexing silicon nitride with optimized properties not only reduces recombination and reflective losses for the front side, but also it can alleviate any color difference after lamination and leading to better aesthetics for the modules. And for metallization, we adopt the so-called super multi-bus bar, which is on the top right side. This technology further reduces the distance between bus bars to minimize the front metal resistive loss. And compared to standard multi-bus bar layout, narrower bus bars are printed with a smaller pitch. Therefore, we can have lower shading loss and also lower resistive loss in the bus bars. And the optical gain can be effectively retained on the module level if we use the super multi-bus bar ribbons when you make the modules. And for fingers, we adopt the kind of the similar approach using the so-called super thin fingers. We optimize the silver paste and cell firing conditions to continuously print thinner fingers with higher aspect ratios on the front side of the wafer. This can reduce the resistive loss in the metal grid, and also it enables smaller finger spacing, therefore higher sheet resistance of the emitter. As can be seen from the evolution chart, among all the technologies developed by for our N-type cells, SE and SE Plus bring about the greatest enhancement in VOC and cell efficiency, while optimizing the front metal grid with super thin finger or super multi-bus bar, further increased cell efficiency with improved JSC and fill factor. And in total, a 0.8% increase in cell efficiency and 12 millivolts in VOC are achieved on average, compared to our previous cell product about 1 year ago. In future, we'll continue to put efforts in the following directions, including further reducing surface and contact recombination, optimizing cell optics, and pushing forward for thinner fingers and use the use of 0BB structure for both efficiency increment and material cost reduction. Our N-type technologies can also be transferred to more advanced cell architectures, such as the back contact cell or the perovskite silicon tantalums. As a professional cell manufacturer, we have the capacity for almost all the common wafer sizes, ranging from standard 1A2 square wafers to rectangular ones, including 1A3, 191, 199 for the longer side. And for standard 172-piece 1A2 modules, the power output can reach 595 watts. And for the same module made with 1A2 times 199, the power output can be as high as 645 watts. And for 66-piece modules with 210 square wafers, our module output can be as high as 725 watts, while for the same module, we still reach 630 watts. Reliability indicators for N-type modules are usually well below the IEC standard of 5%. And our Mono 1 cells, which was released last November, show even improved reliability, mainly for the DH1000. It can be further reduced for both single and double glass modules. As you can see in the chart, the reduction of more than 50% relative can be achieved for double glass modules, while about more than 1% absolute can be achieved for single glass modules. And compared to the standard PERC, N-type modules have higher bifaciality up to 85%, and this can lead to 1 to 1.5% power gain compared to standard PERC. And N-type modules also have better performance thanks to its lower temperature coefficient and slightly lower working temperatures. And this can result in about 2% power gain compared to PERC modules. And moreover, free from light-induced degradation, N-type modules feature lower first-year and annual degradation that may bring about 1.8% power gain with an extra 5-year life expectancy than P-type PERC products. So in summary, N-type modules have the strength of being LID-free, good PID resistance, low encapsulation losses, lower temperature coefficient, better low irradiance response, and consequently much higher power output than the standard PERC modules. As a cell manufacturer, our knowledge about module production is somewhat limited. However, from our research and market feedback, PV modules are experiencing the following changes in our opinion. First, N-type modules are quickly taking up the market for PERC due to their higher power output and lower cost. And second, modules and cells are evolving to approach the most economical size, not only in terms of LCOE minimization, but also considering ingot limitation, logistics, and realistic issues, such as the ease to install or maintain. As a result, 1A2 and 210 cells are becoming increasingly common, with the optimal module height determined to be 2.38 or 1.76 meters. Another important trend we found is the so-called zero bus bar technology. Over the years, PV industry has seen increase in number of bus bars and decrease in bus bar width. Together, they help to reduce front shading and resistive losses in the grid. However, to further reduce silver cost, zero bus bar technology is being developed. It not only saves the cell manufacturers from printing bus bars on cells, but also allows for the use of narrow ribbons and low temperature encapsulation technologies for module suppliers. As a result of less front shading, an increase of about 0.7 to 1% in CTM can be achieved for the modules, and the savings on silver usage can be up to 10% for cell manufacturers, which contributes greatly to LCOE reduction. And moreover, replacement of traditional IR soldering with UV curing of 0BB ribbons can also lead to yield increase. 0BB technology is critical for HET modules, where silver paste makes up a very large proportion of total manufacturing cost. But now it's also being adopted by the TOPCon community. Apart from 0BB, of half-cut cell is also a promising approach to improve module power output. This slide I'd like to share our latest result on half-cut edge passivation, or HEP technology. For lower resistive losses, there's a growing trend for modules consisting of half-cut cells. However, laser cutting introduces silicon dangling bonds and other defects at cell edges, which can cause severe recombination of electron hole pairs. As a result, reduced local minority carrier lifetime and other issues, such as microcracks, can lead to lower pseudo-fill factor and cell efficiency. Generally, a reduction of over 0.5% in fill factor or 0.2% in cell efficiency are observed. To reduce or even fully repair laser damage, we deposit a thin layer of passivation film, such as silicon nitride or aluminum oxide, at the affected cell edge. For batch operation, we can just simply stack hundreds of wafers, half-cut cells together before depositing the passivation film by CVD. An extra test and sort step is highly recommended, which, as I will show later, could further increase module output by reclassifying the half-cut cells into different bins based on their S-passivated characteristics. HEP treatment helps recover pseudo-fill factor primarily, but also may slightly increase VOC depending on how bad the laser cut was. A recovery of about 0.2% in efficiency after HEP is generally expected. And in other words, cell efficiency can be restored to the pre-cut state. As you can see from the table, increment of about 0.2% efficiency is achieved after HEP. And this slide shows module results for HEP technology. For both single and double glass, an increase of about 5 can be achieved. And this corresponds to a CTM increment of 0.8% for standard 72-piece 182 module. And as you can see, the results for single glass module and glass module are quite, so it means that technology is kind of inside. I think it's very important for half-cut cells, for modules made with half-cut cells. It shows the cell efficiency variation after laser cut. Cells from the same bin with a spread of 0.1% efficiency can get more distributed after the laser cut. As you can see in the left-hand side, the graph, it shows two sets of measurements. One is before the laser cut, and the other one after the laser cut. The absolute value is omitted because it's tested on different testers, one for the whole wafer and the other for half cell. But the spread is very real. After laser cut, the spread becomes like 0.3 or 0.4% in efficiency. So it is viable to perform an extra test and sort step for the half-cut cells, as you can see in the right-hand table. And then you can reclassify the half-cut cells into 3 new bins labeled as low, medium, or high, depending on the new efficiency. Even the modules made from the low bin cells have slightly higher power output than the module made with the mixed lot, which is a baseline.
Sure.
And you can note that none of these cells are HEP treated yet, but the trend will be quite similar after HEP.
Hey, sure.
And this slide summarizes the relevant reliability tests we have passed. In general,
Hello, can you hear me?
the HEP treatment does not cause any cell or module reliability issues.
Could you please finish in 1 minute?
So to summarize, HEP treatment leads to higher average cell efficiency, thus more power output for modules. And an extra test and sort step after laser cut and HEP are concentrated characteristics, leading to extra power gain. And meanwhile, cutting into halves also reduces breakage and ER problems because as roughly 40% of the ER problems appear only in 1/2 of the cut cells. In addition, wraparound of the passivation layer, such as silicon nitride or aluminum oxide, does not pose a problem for cell welding or affect module aesthetics upon lamination. And yeah, that's all of my presentation today, and thank you for your attention.
Okay, thank you. I was trying to interrupt you in between, but thanks for closing it soon. So I actually have several questions, but most of them were covered in the chat box. So please try to answer them. But I still would like to ask you one question, like, are you supplying the edge passivated TOPCon cells? Is it your a default, a general offering, or you do it on request?
Sorry, I think volume is below. Please allow me to put my headphones. I think the volume is low from my computer. I don't know why. Could you please repeat the question?
Yeah, are you supplying the edge passivated TOPCon cells, top cells, edge passivated TOPCon cells?
Yeah.
Are you supplying them?
Yes, we are.
Okay. So, yeah, I think your internet is also a little unstable. So could you please stay, and there are a lot of questions in the chat window. Please answer them in the chat window.
Okay, so in the chat.
Yeah, the chat.
Right?
Yeah.
Okay.
Okay. Thank you.